Okay, so hi everyone. Today would be the second session, which we would review the assignments from last day, the real world engineering, math and physics concepts. So the assignment was just prepare a very short presentation on either like non-contact forces or something not so simple math ideas that we did in the last class. So the order of presentation would be Rohana, Gomana, and Shrishti. So you all could begin anytime you're ready. And if I have
Okay,
to like
no problem.
allow any screen share, just tell me, right? I'm not sure. I hopefully you should be able to screen share. I'm not sure.
Okay, I'll try and let you know. Oh, for some reason, oh, okay, don't worry, I got it. You could see it. It's on
Lovely.
gravitational
Yes, we
forces.
could see it, and
Okay,
it is beautiful.
beautiful. Okay, let me just put it in presentation mode. Right, sorry about that. Okay, so I chose non-contact forces, and it's a very short presentation. It's about gravitational forces. So I'm just going to start one time. So, what is a gravitational force? So, a gravitational force is a non-contact force, meaning it acts at a distance without the need for physical contact. And it exists between any two objects that have a mass and always pulls them towards each other. So, it's always an attractive force. And I wrote down, well, typed down some key features of gravitational forces. So we already touched on non-contact, meaning it acts over a distance. It's attractive only, we already mentioned that. It acts on all masses, so every object with a mass exerts and experiences a gravitational force, just like us right now, gravity is pulling us down. And it's universal, meaning that it operates anywhere in the universe. So in your room, on Earth, in space, it's always attractive, never pushing things apart. So let's look at some examples of gravitational force in action. So it could be when dropping objects. So when you drop your own phone, gravity pulls it straight down to the ground. So without the gravity, it would just be floating in midair, which would have probably been good for us because I drop my phone all the time. And that's why I have a crack on the screen. Jumping. When you jump, your legs push upwards, but gravity pulls you right back down. It have some additional ones that I didn't add in the example. So this was one of them. Ocean tides as well. So the moon's gravity, it pulls on the Earth's oceans, causing the rise and fall of sea levels. So that's what we call tides. The planets and orbits. So each orbit, Earth orbits, sorry, the sun because of the sun's gravitational pull. So similarly, the moon stays in orbit around the Earth due to the Earth's gravity. Your body weight as well. Your weight is just basically a force of gravity acting on your body's mass. So if you were on the moon, you would weigh less. I think it's 1/6 that of on Earth, I believe, because the moon's gravity is weaker. And also another one is black holes, actually. That was so cool, so cool. These are regions in space where gravity is so strong that not even light can escape. So those are like that's like an extreme example of how powerful gravity could be when like a mass is concentrated in a tiny area. And obviously, we have to have our boy, Isaac Newton, with all his lovely formulas and laws. So, this is his law of universal gravitation. So, he figured out that gravity isn't something that just pulls apples to the ground, right? It acts between all objects with mass. So, even ones far apart in space. So, his formula is in the corner there, F is equal to G, M1, M2 over R2. So F represents that gravitational force between the objects. M1 and M2 are just, well, masses of two objects. R is the distance between those the centers of those objects, and G is the gravitational constant. So that's that fixed mass value that we have to work with. And well, the stronger the force for two objects, they'll have greater mass. And well, weaker when the objects are further apart, obviously. And well, why is gravity important? I didn't make a slide on that. I should have made a slide on that though, guys. So for it's important because obviously we don't want to be floating all the time, as much as we would want to fly, as great as it would be to fly, is not um really ideal on most occasions. So if the Earth, right, if the Earth became twice as massive, the gravitational force we would feel would like double, and if the moon were twice as far from the Earth, the gravitational pull between them would be 4 times as weaker. That's crazy, yeah? And this law of gravitation, this is how scientists predict how satellites stay in orbit and how much fuel a rocket needs to escape the Earth's gravity and how stars in the galaxy interact across space. So, like, Isaac Newton was like the man. He still is the man because how else we would know how to do all of this? So, yes, that was my presentation. Thank you.
Oh my goodness, it was awesome. Awesome, awesome,
Thank
awesome.
you.
Clap, clap, clap. I did learn a lot. I love that you included like the physics concepts, and then you also included some of Blake's not so simple math with the without the the equation. It was excellent, fantastic job. Commander, you could start anytime you're ready. Commander, I'm not sure if your mic is muted, right? But we could see the presentation.
Okay, so hi everyone. Today I will talk about the physics behind wireless charging. So if anyone not familiar with wireless charging, basically it's a way to charge devices like phones without using any physical wires. It's actually a great example of non-contact force, specifically electromagnetic force. So let's see how it works. Wireless charging works through a process called electromagnetic induction, based on something called Faraday's law. This law says when a magnetic field changes near a coil, it creates an electric voltage. The formula is EMF equal negative and d phi by dt. I can explain it. EMF is a voltage created, N is the number of turns in the coil, and d phi by dt is how fast the magnetic field is changing. So inside the charger, there is a coil that carries the alternating current, which makes a changing magnetic field. That field travels through the air, and the coil inside the phone catches it, creating a voltage. And that's how your phone gets charged. We can see now the components and the forces it used. There are two important parts: the transmitter coil inside the charger, which makes the magnetic field, and the receiver coil inside the phone, which pick up the magnetic field and turns it into a electric current. And of course, everything in life have pros and cons. So the pros of the wireless charger, it's super convenient, and there is no need for cables, and many devices now are waterproof. But the cons are It's usually slower than wired charging, and it needs phone to be aligned exactly right, and it only works at a short distances. So here is a real word it uses. We can use it in many places or many devices like phones, smartwatch, wireless earbuds, and even electric cars. You can find wireless charging stations in airports, cafes, and even inside furniture like IKEA. And some medical devices like pacemakers use it too, because it's safer and as there is no need for wires inside the body. And here's a fun fact I forgot to add to the slide. Nikola Tesla thought of this idea over 100 years ago. He dreamed of sending electricity through the air, and now we are finally doing it. And that's all. Thank you for listening.
Yay, that was so excellent. Oh my goodness. Everything there was completely new to me. Like that entire presentation, I was just learning. It was so awesome. You sound like a true scientist. It was so awesome. Um, Trishti, anytime you're ready, you could start.
Okay, so after two amazing presentations, I don't know if mine will be up to the same standard, but I will try my best. Are you all able to see my screen?
Yes.
Okay. So my presentation is also on a non-contact force, and that is electrostatic force. So this is the basic definition of electrostatic force, and basically it's an attractive or repulsive force. Remember, we learned that a force could be a push or a pull, meaning that it could push you like and two objects which experience this force, it could cause them to repel each other, as in, it would be difficult to bring them closer, or they could attract, where, they have such a high tendency to move towards each other. Um, Now, this force could act over a distance, so that is what makes it a non contact force. And it's also notable that when we hear it, when we say electrostatic, we think electricity, and that is because it deals with electrically charged objects. So this is why electrostatic force is a non-contact force, and that is because two charged objects, they don't necessarily need to touch or be in contact to experience this attractive or repulsive force. Now, this is just a little background information, which I'm sure we might know already, but just to reinforce it, we have two types of charges, positive or negative. Now, we could have a neutrally charged object, meaning that the number of positive ions is equal to the number of negative ions, and that would mean that it's neither positive or negative. But in dealing with objects that experience electrostatic force, they will either be positive or negatively charged. Now, if an object is positively charged, that means that we have less negative charges than positive charges, and we have like an overall positive charge. And when we have a negatively charged object, that means that the number of positive charges is less than the number of negative charged ions, I should say, in the object. And opposite charges attract, so positive attracts negative and so on. And like charges, let's say you have two positively charged objects, they will repel. Now this is on a side note, so we have like an image of an atom here. um, Protons are the positive ions in an atom, and they are bound by the nucleus of the atom. Now that kind of prohibits them from moving about like electrons would be able to. Now, we should also know that electrons, while they are attracted to the nucleus and that will hold them in place, that force is not always strong enough to hold them within the atom, and they may not always stay attached. So in cases like if you rub two objects together, we do have the movement of electrons, but you will see in different textbooks and in this presentation that we will also talk, and we will always talk about electrons or negatively charged ions moving and not really the positively charged ones, and this is why. So I have some examples, and you would find that these are things you encounter in your everyday life. Let's say we have a charged polythene rod, and if you were to bring that near to a dry paper, no, not touching, but just near to it, the rod would have a net negative charge, whereas the paper will be neutral. So, as I mentioned before, when it's neutral, equal number of positive and negative charges. Now, since like charges repel, remember we have electrons close to the rod. Now, they would move away from that area that is closest to the rod and move to like the opposite side of the paper, and that is an example of electrostatic force, because when they move away, then we have a positive charge there. And the positive charge of the paper in that region and the negative charge of the rod will cause them to be attracted to each other. And we have an attractive force there. And note again that the two objects do not need to touch for this to happen. So that's why it's a non contact force. Now we have another example. I'm not a huge fan of doing laundry, but I have encountered this scenario before. So sometimes if you have a dryer and you put clothes in it, when you take it out and it's dry, you will notice that clothes stick together. So basically in the dryer, sometimes the clothes will rub against each other because they're spinning around so quickly, and that's bound to happen. And there will be a transfer of electrons between objects, and that will cause objects to have different charges, either positively or negatively charged objects. Now, some will be positive, others will be negative, and that is what will cause them to be attracted. And that also, in this scenario, we see static electricity, but we also see electrostatic force. So I think this also shows that physics and science exists all around us, and we don't necessarily need to be in a lab to experience and see how it works. So I hope you all will think more about physics when you encounter these things and be able to understand it better. And that's the end of my presentation. Thanks for listening.
Wow, wow, wow. It was amazing. That was very, very like well put together, and it was awesome. Very, very awesome. I don't know. It's something about like electrostatic forces and like I don't know, magnetic forces. I always just love it. It was so, so great. Um, Blake, I'm not sure if you want to, you know, say anything.
Yeah, that was great. I've always wondered why clothes are prone to sticking together during laundry, and that totally makes sense with the van der Waals reactions between the atoms on each thing. And yeah, so everyone, you guys all had great presentations, and it was very quite fascinating and interesting to listen to all of them.
Yes, thank you guys so, so much for all like participating and doing the presentation. I know for the past like well since the week started, every day there was like a meeting every day, and you all still found time to make like these beautiful, wonderful, informative presentations. You all are so amazing. Great, great job. And well that would be the end of today's meeting. It was very lovely getting to hear from you guys. You all are so smart and so brilliant and continue being awesome.